Hi guys, this is the fifth video of the Dynamic Programming Algorithms video series. So far, I introduced the short spat problem and talked about three different algorithms to solve this problem in the previous videos. These algorithms were Dijkstra's, Bellman-Ford and Floyd-Warshall algorithms. In this video, I will compare these three algorithms in terms of their time complexity, space complexity and capability. Let's start with Dijkstra's algorithm. Here, I am skipping the implementation details of this algorithm. If you want to learn more about it, I recommend you watch the second video of this video series by clicking the link above. Let's recall the Python code of the algorithm. The first part, where we initialize adjacent nodes dictionary, is just to make things clear and more understandable. Instead of creating such a dictionary, we could provide edges dictionary in that format as an input so that we will not need this step inside the function. So, disregarding this part, let's start the time complexity analysis. Initializing the short spat distances takes order of v time, where v is the number of nodes. Then we have a while loop which repeats v times, as the length of temporary node list is v, and we remove one element at each iteration. In this loop, we find the node with minimum path length and remove it from temporary nodes list. For now, let's suppose that it takes ts times per iteration, where s represents the first letter of search. We will discuss the possible value of ts for different data structures in a bit. Then we have another loop which we update the path lengths. This loop is over each adjacent node of u. Since different node u's iterate in the while loop, considering the outer and inner loops together, the path length update operation repeats e times, where e is the number of edges. For now, let's say that the update takes tu times per iteration, where u represents the first letter of update. So the time complexity of Dijkstra's algorithm is order of v plus v times ts and plus e times tu. We can write it in this way so that it's equal to order of v times ts plus e times tu. Let's consider the possible data structures to find the complexities of finding and removing the minimum, as well as updating the short spats. Here we compare the worst case scenarios. The first option is using a hash map. It's basically mapping keys to values, like using a dictionary in Python. In this case, ts and tu are order of v. If we use a sorted array, like an ordered list in Python, we can easily identify the minimum value in the list, so that the complexity of ts is just order of 1. For an AVL tree, which is a self-balancing binary search tree, the complexity is order of log v for both ts and tu. Lastly, for Fibonacci heaps, which is a collection of heap order trees, the complexity is order of log v for ts, whereas it's order of 1 for tu. There are also other data structures we can use like binary heap or hybrid version of it, but I don't cover them here as they are not the best choices. The resulting time complexities for Dijkstra's algorithm are as follows. Since log of v less than v, Fibonacci heap seems the best option in terms of the time complexity. In terms of the space complexity, we just need a space of v, as we need to store the shortest path length for each node. Next, let's find out the time and space complexities of Bellman-Ford algorithm. Again, I am skipping the implementation details. If you want to learn more about it, I recommend you watch the third video of this video series by clicking the link above. Let's recall the Python code of the algorithm. Again, as in Dijkstra's algorithm, initializing the short spat distances take order of v time. Then we have two loops, one over the nodes and the other one over edges. In these loops, we update the short spat length. As we just showed that this update per iteration can be done in order of 1 time, the time complexity of this part is just order of v times e. Lastly, while checking the existence of any negative weight cycle, it takes order of v time as we iterate over each edge. So, the time complexity of Bellman-Ford algorithm is order of v plus v times e plus e, which is equal to order of v times e. Again, as in Dijkstra's algorithm, we just need a space of v, as we need to store the short spat length for each node. Lastly, let's take a look at Floyd-Warshall algorithm. If you want to learn more about the implementation of this algorithm, I recommend you watch the fourth video of this video series by clicking the link above. Here is its Python code. In the first part, we initialize the shortest path length from each node to another one, which takes order of v squared time. Then we have three nested loops, each iterates v times. In each iteration, we update the path length. So in total, this part takes order of v cubed times. Lastly, checking whether the graph has a negative weight cycle takes order of v time. In total, the time complexity of Floyd-Warshall algorithm is order of v squared plus v cubed plus v, which is equal to order of v cubed. As we store the shortest path length of each pair of nodes, the space complexity is order of v squared. This completes the time and space complexities of the algorithms. Here is the table summarizing the performances of the algorithms. Before comparing them, let me talk about the relation between the number of nodes v and number of edges e. First, e is always greater than v, as a graph has more edges than nodes. Then, e is order of v squared in the extreme case. More specifically, e is equal to v times v minus 1 in a complete graph, where all node pairs are connected. So it is safe to assume that we prefer order of e over order of v squared. If the graph has no negative weight edge, then it's best to use Dijkstra's algorithm. It's because it asymptotically performs better than Bellman-Ford and Floyd-Warshall algorithm, even we need to calculate the shortest path length between all node pairs. If the graph has negative weight edge, then we cannot use Dijkstra's algorithm as it fails. In the case that we want to find the shortest path length from a single source node to other nodes, Bellman-Ford algorithm asymptotically performs better than Floyd-Warshall algorithm, because we prefer order of e over order of v squared. On the other hand, if we want to find the shortest path length between all node pairs, then Floyd-Warshall algorithm would be the best choice as e is greater than v. This concludes our comparison. In this video, I compared 3 different algorithms to solve the shortest path problem. The comparison was based on the time complexity, space complexity, and capability. I hope that it was helpful. Please leave a comment if you have any question. In the next video of this dynamic programming video series, I will introduce the knapsack problem and show how to solve it by using dynamic programming.